Okay, this lecture is specific to Conceptual Physics AB. It continues with sound. Specifically, in this lecture, we'll take a look at a couple of example problems involving intensity, the intensity of sound waves. Go ahead and copy down the first example here into your notes as I read it to you. Okay, a source of sound has a power output of 5 times 10 to the minus 7 watts. Notice how small that number is. When you're talking about relatively low volume sounds, the amount of energy associated with such sound waves is very small. So what we're given here initially in this problem is that P source, as it's called, is 5 times 10 to the minus 7 watts. Okay, and then in this example, we'll look at a couple of things. First of all, in part A, how far from the source must a person be to hear an intensity of 1 times 10 to the minus 9 watts per meter squared, which corresponds to 30 decibels. So we're talking about the production of sound here in part A of the example. Okay, so let's go ahead and draw a spherical sound wave like so. Right here is the source of sound. It has the power output P source as described above. Right here is the radius R associated with that sound wave. What we're asked to find in part A of the problem is R. Now we have an observer, for example, here, and that person is hearing an intensity of this sound wave as 1 times 10 to the minus 9 watts per meter squared, which, as it says in the problem, corresponds to 30 decibels. 30 decibels is like conversational voice. So how far away from the source do we have to be such that we're hearing this sound? So we're going to go ahead and write intensity as P source divided by the surface area of the sound wave, the surface area of a sphere, that is 4 pi r squared. And now what we're going to do is cross multiply and just solve for r squared and then take the square root of both sides. So let's cross multiply the I and the r squared like so. Like this. Now let's go ahead and take the square root of both sides then to solve for the radius. Okay, so this is the radius of the sphere. And I'm going to have to obtain my calculator here in order to make this calculation. Let me grab my calculator. Okay, so underneath the radical sign, we first of all have P source, 5 times 10 to the minus 7 watts. And then we divide by 4 pi times I. So I'll use parentheses, 4 times pi times the intensity of 1 times 10 to the minus 9 watts per meter squared. Okay, take the square root of the whole thing, and we end up with a distance of about 6.3 meters. So it's like on the other side of the room, for example, if I'm talking here with my lecture voice is louder than conversational voice. However, if you're on the other side of the room, you would be hearing an intensity that corresponds to conversational voice, about 30 decibels. So this is 6.3 meters as the answer. Okay, now in part B of the example, we're going to see exactly how the inverse square law works. What would the intensity be at a distance that is twice as far? Okay, so we now have a new radius here. I'm going to call this r prime just to give it a name, and it's equal to 2 times the old radius r. Once again, we found r in part A of the problem to be 6.3 meters. Okay, now the intensity here in this case, I'll call it I prime. This is equal to P source. It's the same source of sound, but now divided by 4 pi r prime squared, like so, where r prime is twice as much as the original value. Let's go ahead and plug this quantity here in for r prime and see what happens. So P source divided by 4 pi times now quantity 2r squared. If you square the parentheses there, square the 2, you end up with a 4. So this is 1/4 of this quantity. Like so. And if you take a look on the top board, we already, of course, know what this quantity is. This quantity here on the top board is equal to the original intensity I. So the new intensity I prime is 1/4 of the original value. Once again, this is how the inverse square law works. If you move twice as far away, the intensity of the sound is 1/4 of the original value. If you would move 3 times further away, it's 1/9 of the original value, and so on. So the answer here is 1/4 of the original value of I. This is 0.25, I'll just write it like that, times 10 to the minus 9 watts per meter squared, like so. Once again, that's the basic idea as to how the inverse square law works. Okay, now for the second and last example, as I said a little while ago, the amount of energy associated with sound waves at relatively low volumes is next to nothing. So I'll give you an idea of that in the next portion of the example, or the next example that is. Okay, let me go ahead and move it here into my screen. Okay, let me do a little bit of erasing here for the next example. Okay, now, a person is 3 meters from a point source of sound. So we're given R in this example. This is given to us as 3 meters. Okay, sound waves reach the person with an intensity of 1 times 10 to the minus 8 watts per meter squared. That's 40 decibels, which is fairly loud. So the intensity I is 1 times 10 to the minus 8 watts per meter squared. Okay, part A of the problem, similar to the last example. In this case, what we're asked to do in part A is to calculate the power output of the source. So I'm going to go ahead and write the intensity I as P source divided by 4 pi r squared. In this case, we're just solving for P source. So cross multiply the 4 pi r squared to the other side. Like so. And now I'll just do the math here, and when I do, I end up with an answer in terms of watts. Okay, so the intensity is 1 times 10 to the minus 8 times 4 times pi, and then times 3 squared. And ultimately, this ends up being about 1.13 times 10 to the minus 6 watts. So this is the energy necessary per second to produce this sound, and notice how small the number is, even though the sound itself at 40 decibels is fairly loud. Once again, the energy associated with sound waves at relatively low volumes is pretty small. We're getting an idea of that here in this example. Okay, let me move my file for the remainder of the example. Okay, now in part B of the example, now we're going to talk about the observer standing over here receiving the sound. Okay, this person's ear, think of it as a box, has a cross-sectional area A associated with it. And in part B of the example, we are given the following. It says that the person's ear has a cross-sectional area of 5 times 10 to the minus 5 meters squared. That's an accurate number. How many joules of energy pass through the ear per second? So what we're calculating here in part B of the example is P receive. Now we'll think of the intensity of this sound. It's still this value, by the way, but now we'll think of the intensity of the sound here for part B of the example as being equal to P receive divided by area A. And now I'll cross multiply the area to the other side and solve for P receive. So this is how much energy per second passes through the person's ear. So it's equal to the intensity I of 1 times 10 to the minus 8 watts per meter squared, and then we multiply by the cross-sectional area of the person's ear. And this comes out to be an extremely small number. It's 5 times 10 to the minus 13 watts. That's 0.5 trillionth of a watt per second that is passing through, of a watt, excuse me, that is passing through the person's ear. And then in part C of the problem, it says, how long would the person have to be continuously exposed to this sound in order to receive a total of just 1 joule of energy? 1 joule of energy is about the energy necessary for me to take the calculator and raise it like this above the desk. So if you were sitting here listening to this sound continuously, how long would you have to stand there to get 1 joule of energy? A couple of minutes, a couple of hours? What do you think? Well, let's see. Okay, now specifically for part C of the problem, we're going to write the P receive here as the energy received per time, where the energy received is given to us in the example as just 1 joule. And now what we'll do is we'll just solve for the time. So cross multiply, and the time is E over P receive, where E once again is just 1 joule, and P receive is what we calculated earlier. So let me go ahead and do this calculation for us, and you end up with 2 times 10 to the 12th seconds. That's 2 trillion seconds, which is a long period of time. Just to give you an idea as to how big this number is, it's much larger than a human lifetime. Let me go ahead and convert it for us into years. There are 3.15 times 10 to the 7th seconds in a year. So if I divide by 3.15 times 10 to the 7th seconds per year, you end up with like 63,492 years. Once again, the energy associated with sound waves at relatively low volumes such as this is next to nothing. So we got a nice idea of that here with part C in the example in particular.